So in this lecture, we'll go for few examples, how to solve examples on 2 degree of freedom system. So let us start with the first example. Let's say it is given, determine the natural frequency of torsional vibrations of a shaft with two circular discs of of uniform thickness at the ends. The masses of the disc are, let's say, M1 is 500 kg and M2 is 1000 kg, and their outer diameter are D1 125 centimeter and D2 is 190 centimeter. Now the length of the shaft is L, which is equal to 300 centimeter, and its diameter D is 10 centimeter. Modulus of rigidity for the shaft material uh, G is 0.83 into 10 to the power 11 Newton per meter square. Okay. And um, it is given that also find in what proportion will the natural frequency of this shaft will change if along half the length of the shaft The diameter is increased from 10 centimeter to 20 centimeter. Okay. So this is the question. The schematic is like this. Diameter D1, mass M1, diameter D2, mass M2, length L, diameter D at the start. And the given data M1 500 kg, D1 is 1.25 meter, M2 is 1000 kg, D2 is 1.9 meter, and shaft length L, it is given 300 centimeter, that is 3 meter. Dia of shaft D is 0.1 meter, and modulus of rigidity for the shaft 0.83 into 10 to the power 11 Newton per meter square. These are the given data. Okay. Now we can have the moment of inertia of first this J1 will be M1 R1 square by 2. Okay. So we'll have 500 into 1.25 is the diameter by 2, which is the radius, then square divided by 2. So it will be approximately 97.65, or we'll take this as 98 kg meter square. Then further J2 will be M2 R2 square divided by 2. So we'll have 1000 into 1.9 by 2 square by 2. So this will be 451.25 kg meter square, right? Then we have this KT is equal to G dot IP divided by L is 0.83 into 10 to the power 11, then length is 3 meter, then IP, the polar moment of inertia of the shaft, will be 0.1 to the power 4. Okay, we will multiply pi 4 divided by, because it is pi d4 by 32, no? So it will be equal to 2.716 into 10 to the power 5 Newton meter per radian. Okay. Now the equation of natural frequency, we have the equation of natural frequency omega n will be kt J1 plus J2 as we have derived earlier, divided by j1 j2 root over. Okay, so this will give us 2.716 into 10 to the 5 whole into 98 plus 451.25 divided by 98 into 451.25 whole root over. Okay. So this will be equal to 58.08 radian per second. So we can have the natural frequency Fm as omega n by 2 pi. So 58.08 by 2 pi will give us 9.24 hertz. This is the answer. Now, a second example. It is given that determine the natural frequencies and mode shape of the terminal system as shown in the figure. Take uh, sorry, take I1 equal to I and I2 equal to 2I, and this KT1 is equal to KT2 as K. Now the schematic is like this. Now we have the shaft up to this portion. Let's say this is KT1, this is KT2, this is I1 and I2. You have to find out the natural frequency and mode shape. Now let theta1 and theta2 are the angular displacements of I1 and I2 respectively. Okay. The equation of motion can be written as uh, I1 theta1 double dot plus KT1 theta1 plus KT2 theta1 minus theta2 is equal to 0. I2 theta 2 double dot plus k t2 theta 2 minus theta 1 is equal to 0. Let's say this is first set of equation. Now rearranging and substituting I1 equal to I2 as 2I and KT1 is equal to KT2 as K. We'll have the equation as I theta 1 double dot plus 2K theta 1 is equal to K theta 2 and 2I theta 2 double dot plus K theta 2 is equal to K theta 1. Let's say this is equation 2. Okay. Uh, assuming assuming the steady state solution for principal mode of vibration uh, theta 1 as beta 1 sin omega t and theta 2 as beta 2 sin omega t. Let's say this is equation 3. We'll have theta 1 dot will be omega beta 1 cos omega t and theta 1 double dot will be minus omega square beta 1 sin omega t and theta 2 dot will be omega b2 cos omega t and theta 2 double dot will be minus omega square beta 2 sin omega t. Let's say this is equation 4. Okay. Now substituting the values of theta in equation 2, now we'll have minus I omega square beta 1 sin omega t plus 2k beta 1 sin omega t is equal to k beta 2 sin omega t minus 2I omega square beta 2 sin omega t plus k beta 2 sin omega t is equal to k beta 1 sin omega t. Let's say this is equation 5. So to further simplify this, we'll have minus I omega square plus 2k beta 1 is equal to k beta 2 and minus 2I omega square plus k beta 2 is equal to k beta 1, right? Let's say this is equation 6. Now from equation 6, we'll have two ratios of beta 1 and beta 2. One will be equal to k by 2k minus I omega square, and the other beta 1 by beta 2 will be equal to k minus 2I omega square by k. Let's say this is equation 7, this is equation 8. Now equating equation 7 and 8, we'll have k by 2k minus I omega square minus k minus sorry is equal to k minus 2I omega square by k. So this will give us 2k square minus 4k I omega square minus ki minus ki omega square plus 2I square omega to the power 4 is equal to k square. So this will be equal to 2I square omega to the power 4 minus 5ki omega square plus k square is equal to 0. Let's say this is equation 9. Okay. So solving equation 9, we have omega square will be equal to 5ki minus plus root over of 5ki square minus 4 2I square k square divided by 4I square, or we can say omega square is 5ki minus plus 17ki root over divided by 4I square. Let's say this is equation 10. Now this will give us two values of natural frequency. Omega n1 will be 5 minus root 17 k by 4I whole root over, and omega n2 will be 5 plus root 17 k by 4I root over radian per second. And the mode shapes are beta 1 by beta 2 for the first mode will be equal to k minus 2I omega square divided by k, that is 1 minus 5 minus root 17, 1 by 2, so that is 0.561, and beta 1 by beta 2 for the second mode will be k minus 2I omega square by k is equal to 1 plus, sorry, 1 minus 5 plus root 17 by half, so it will be minus 3.561. This is the answer. Okay, so in this way we can solve the problems related to